So how do we deal with this floating pin problem? What happens if we're not touching the button? If we're not touching the button, we want the button to be at 0 to say, hey, look, no one's touching it, right? But that's clearly not what's happening because it's just floating. So if you remember, the kind of insight for this is like when we had these resistive sensors that only had 2 legs, we had to add in that resistor to make them into 3 legs, a 3-legged resistive sensor. We sort of have to do the same thing with these buttons. And so that's what we're going to do. So let's see, I have a resistor pack here, and I've already pulled out some 10K resistors, and that's what we're going to do. We're going to use a resistor, and in this case, in the circuit, it's going to be called a pull-down resistor because it's going to pull the value down to 0 volts when we're not pressing a button. So we're going to add in this resistor. And rather than having the yellow wire connect directly to the black, we're going to first have the resistor connect to this 10K resistor connect to the black. And then we're going to have the yellow alligator clip connect to the other side of the resistor. And already, guess what? You can see that it's pulled down. You can see that it's pulled down. So I just disconnected it. Now it's floating. But if I connect it over to this resistor, boom, it's pulled down to the default state, which is saying no one's pressing the button. Now let's say someone comes over and they press your button. Boop. So let's simulate that by connecting the red alligator clip. Boom. Now it's pulled up to 3.3 volts and the button is pressed. As you can see that the red lights go off. Boom. So we can connect, we can disconnect, and so on. So let me make a little diagram of what that looks like. So let me make a little diagram for what that looks like and maybe give you a bit of intuition about what's happening. So I'll move this for now. And the other thing is I actually have, if you want to go into this in detail, and I'm just going to talk a little bit about the circuit and physics behind this, but I do have this on our physical computing website. I go into this in fairly great detail on this floating pin problem and pull down resistors. And so if you want to have more detail, you can look at this. It's hooking up digital input with microcontrollers, and it's called the floating pin problem. And you get to see a video of me causing interference on the button and how to solve this. But I'm going to walk you through it right here on this pad. So essentially what we were doing before, the question is like, well, what is a button? So we had 3.3 volts. And let's just say this is our button. And when the button closes, then the electrons can flow, the charge can flow. And this went to ground. So this went to 3.3 volts, this went to ground. And of course, we've got to do our A1. So this goes to A1 on our CPX. So what happens right now? A1 is connected to ground. So that's like when the yellow alligator clips are directly connected to the black alligator clips. And so A1 will be equal to 0 volts in this current state. But if we close the button, now A1 is going to be equal to, oh, well, guess what? Not good. A1 will be equal to 3.3 volts. But we have this is a short circuit. And your CPX, remember we said never connect the red wire to the black wire? Well, that's exactly what happened when we closed this button. So how do we deal with that? Well, guess what? The pull down resistor. So let me rebuild this button here. Boop. It's like a switch. Closes up. You push it, the switch closes. So now let's add in our friendly 10K resistor right here. 10K. This will work. This is our pull down resistor. Which pulls down the input in its current state when the gate is open or when the switch is open to 0 volts. And then when you press the switch, switch pressed, it goes to 3.3 volts. And we no longer have a short here because we added in this pull down resistor. The current in your circuit is going this way. So they usually write current as I. There's very minimal current that's going that way. So you're measuring voltage on A1, as we talked about with the analog input. But it's okay if you don't really get this and understand the underlying physics. What's important here is the configuration of this circuit. That you need to have a pull-down resistor if you're going to use a button. And we'll find out in maybe the next video, depending on how I edit this, how to do this without actually adding in a pull-down resistor, because internally in the CPX there's something called an internal pull-up resistor. So it flips the logic, but it does make the circuit easier. But for now, we're just going to use these 10K resistors, pull them out, and we're going to use them to hook up to our first button, which looks like this. So we're going to probably wire wrap it because I don't want to introduce a breadboard yet. And we'll set up that circuit. All right. So the interesting thing about these buttons, and we will give them out in class, they're super cheap and pervasive. You've probably seen them before when you're interacting with stuff. They've got a nice tactile feel, they're spring loaded, and in fact, with the joysticks that we have been talking about, there's a built-in button right there, and it's just a smaller version of this. All right, so it has 4 legs, which students oftentimes find confusing. So we'll just use one of these, and I can use, if you have access to a multimeter, this is a great tool to figure out which legs go where. So this multimeter has a short circuit detector that will buzz when the red and black wires touch. Listen. But we can use that to determine which parts of this button are connected when the button is depressed. So we're going to set it up like this. I'm going to set it up like this. So when the button is not pressed, we don't hear anything. But now watch, I'm going to press the button. All right, so that means that these 2 parts of the button are connected, are shorted when the button is pressed. So let me make a little diagram. Because it is kind of confusing. So we have, let's see, we have our button, just like this. And we have a bolt here, a bolt here, a bolt here, a bolt here, just drawing it out. And then we have a leg, and a leg, and a leg, and a leg. Now, intuitively, it kind of looks like a face. Now, intuitively, a lot of students think that if you press this button down, that this leg will connect to that leg, but that's not actually what happens. Instead, it's these two get connected, and these two get connected. All right, so so we have our button just like that, and again, I can show that to be the case. I will hook up the button exactly in this configuration now. It's just like this. I'm gonna make that blue part a little bit bigger. Maybe make it a little 3D. All right, so when we press this down, it's gonna buzz. Now, if I move this over here, this is constantly connected on the top side. So that doesn't work very well as a button. I can move it down over here, and again, it'll work. So you just have to be clear about which of these legs are connected when the button is pressed. And I can show you how to do this without a multimeter as well, when we just hook it up to MakeCode and the graphs, and we can sort of see stuff. All right, so I'm going to first hook it up without that pull-down resistor. We'll see what happens, and then I'll hook it up with the pull-down resistor. And we can use the same code as before. So I guess here it is. So let's say that you just hook up the yellow to one leg and the red to the other, all right, like that. So that would be equivalent of what I did was I just hooked up that to 3.3 volts, and I hooked this up to A1. All right, and you can already see that it's in an indeterminate state when the button isn't pressed, which is why we need the pull-down resistor. But let's take a look at the graph as well and MakeCode. And then when I press it, it will go to 3.3 volts. So now it is at 3.3 volts, and I let go, and it starts to go haywire again. But if I press it, that works. It's just when you're not pressing the button, it's in this indeterminate state, and it's the floating pin problem. So I'm going to wire wrap and generally you would be using a breadboard for prototyping these circuits, but I'm just wire wrapping like this. Oh, can you see that? Like that. And now I'm going to add the black wire to the bottom of this, just like we have in the diagram. Okay, ground is here. And we're going to hook yellow up directly. So we've got now these 3 prongs on the button, just like our diagram. It's the exact, I'm just mimicking it. The ground is getting pulled. This pull-down resistor is pulling down the input signal when the button isn't pressed to 0 volts. So I've just replicated that circuit, right? And now if I press the button, it goes immediately up to 3.3 volts, and if I release, it goes down. Look at that. There we go. Perfect. So our first button. This is amazing. And you learned how to use a pull-down resistor. Now, what you've all been waiting for, I'm sure, is playing Flappy Bird. So let's modify our code. Boop. Let's modify our code. So we could save this as digital versus analog input and save it. All right. Whoop. There we go. So let's start over, and this time we're going to use the button press to play Flappy Bird or some single input game. So go back to pins, digital read pin. We're going to go to this logic. If digital read pin, remember on A1, and we're also going to have to make that variable, although we don't really need the variable in this case. So but we want to turn on the lights. This is if digital read pin A1 is being pressed, it's at 3.3 volts, then we'll turn on the neopixels. Else, we will turn them off. And then how do we make this into mouse input or keyboard input? Either one would work, because we could send like a space bar, but I'm going to use the mouse. And now we have mouse here, and say mouse button left. I'm going to use the left click there. So mouse button left down when the button is down. Copy paste that. Mouse button left up. So that's it. And let's go download that. And there's actually no console output here because we didn't use console. So if you want to like debug it and still have console output, that might be valuable. But we can also just test it by hitting the button. And let's open up Flappy Bird. Let's see. Chrome. There are these websites with Flappy Bird. Flappy Bird. Flappybird.io. Okay, I already lost. But look at that. Now I'm using, I guess you can't really see that I'm using the button. I've got to, all right. Now I will restart this. And there we go. Let's see, move this. Oh my gosh, so many ads. Are you serious? All right, so many ads. Forgive the ads. There we go. Just using the button. Can I get past 1? Oh man, no, I guess I can't. Restart. Here we go. Come on. Oh, this is really fairly difficult. Okay, I'm gonna get there. Oh. All right, last time maybe? Because I know I can do it. It's actually, okay, I honestly didn't fight that time. Maybe we got to do it for the Okay. Yes! We could always use mine, although I think mine takes keyboard input, which I guess we could quickly show. So this is like so I'm saving the file now. This is A1 digital input mouse. So we can make a version of this. Oops, I misspelled that. A1 digital input mouse. I'm going to duplicate that. I'm going to call it digital input keyboard. And we'll send it a spacebar instead. So is this the one I just made? I think so. So rather than doing mouse, we're going to do keyboard. And so we're going to go back to extensions, keyboard, keyboard type, I think would be fine. So that will send a fair number. Well, we'll see how this goes. Just make sure there's a space in there. So it's sending a space. You can see if digital read is high, 3.3 volts, it sends. All right, so we'll just try that. Oh, and we have no way of turning this on or off. So I think we got to do the slide switch trick like we did before. So input on switch moved left. Or actually, okay. We can do another if. This way I can control whether or not this thing is on. If switch right. So now if the switch is right, then I will send them something. And I'm going to just change the color. So we'll do like a blue. All right, so if the switch is to the right and I hit the button, it'll turn blue. If the switch is to the left, on the button press, it'll just be red. And that way we can differentiate and be like, oh yeah, I know I sent a space bar because it turned blue. So let's download. And we can just open up Notepad. Gotta find my mouse. So pressing the button, but it's turning red. Oh, okay, so let's see, I'll switch it over. There we go. So that's, yeah, very fast. So we could modify this to make it better, but let's just check this out on Flappy Bird and see how it goes. Anything else? No, I think we're good. So let's open up my Flappy Bird. P5JS. I'm just going to log in as me, and I have some Flappy Bird. There we go. And I have it using spacebar, so whoa. All right. I'm kind of in the way. You can't even see me press the button, but I am. Here we go. Let's try it again. Okay. This is partly because we just keep sending it. So we could modify the code to make this a little bit. Oh, but I'm much better at my version of the game. All right, so yeah, so we're gonna slightly change our make code to rather than do keyboard type, I think we're gonna do keyboard, and I'm gonna turn off, just like this doesn't bother. So I just moved the switch to the left. Keyboard key press down. Keyboard key press up. And just, I always go back into JavaScript when I'm working with these spaces because it's not clear from the block whether or not I'm sending the space. So I am sending a space, key down, and then key up. And remember, this looks a little bit more complicated than usual because I have a double if block. I'm saying if the digital read, if you're pressing that external button, but I'm only sending the keyboard key if the switch is to the right. And that way I can control whether or not I'm using my CPX as a controller or not. All right, so let's download this. Didn't go directly to the board. I might have to bring it over. That time it looks like it worked. Yeah. All right, let's go back to my game. All right, yeah, so now, okay. So now it's working far more like a space bar would. and I'm using the button, but you can't tell, and I'm doing so well I don't really want to die. But let me just refresh this. We'll move it over, I guess, like that, and this way you can see. You can see me play. All right. So let's get it. Boom, 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 boom. Oh, sure. Yeah. I could post the code to this too. I've shown this in class, but probably the first time I've shown it on video. Yep, much better with my Flappy Bird. Maybe this is just easier. The pipes certainly are bigger. Oh, and I would have kept going, but it got disconnected, which is a good reason why to use a breadboard for this. But we did it. I showed you digital input. The next video, I think I'll show you how to hook up some of these arcade buttons, maybe this big button, and possibly we'll work on the joystick as well at some point. All right, very good, prototypers. See you next time.